One of the biggest problems with making animated videos is that they take a really long time to make. Sometimes I can spend upwards of several hours on an animation that's literally on screen for just like 10 seconds. And so if there's a lot of material you want to cover, it's not really possible to make animations for every single thing in a reasonable amount of time. And so I asked you guys if you'd be interested in kind of a more unedited, simple explanation of some of these ideas before I have time to make a full animation on them, and you said yeah. So here we are. Today we're going to be talking about the basic ideas of thermodynamics, kind of some of the concepts that are useful if you want to start studying. It's almost like terminology and the basic ideas. So this would almost be kind of like what you'd see in the first week or so of a course. And where it really all starts out is systems. So there are two kinds of systems that we look at in thermodynamics. So you have open and we have closed. So closed system means it has no mass transfer. And an open system, I'm sure you can figure out, means that it does have mass transfer. So when we're looking at an open system, basically we're going to say, all right, well, let's look at these. Maybe I have an x and y. This is the x-axis. X and y coordinate system, and I have some kind of volume that I'm looking at. Open systems are also called control volumes because we're looking at basically some kind of volume in space. And I can be like, okay, well, maybe I'll let some mass come into here. Maybe some mass can come out. It doesn't really matter. I'm just going to be looking at this point in space. Now, closed system, on the other hand, says, all right, I know I have some mass, and I'm going to analyze what happens to this mass. Maybe there's some forces. Maybe there's some displacement. All things can happen. But I'm just going to see what happens to this mass. So this is the kind of system that you would see in a general kind of like classical mechanics or a physics class. An open system is more something you'd see in thermodynamics where you have fluid flow and things like that. I'm assuming you'd also see it in like a fluids class. Now you can also break open a closed system into what's called an isolated system and just a normal closed system. And an isolated means that on top of no mass transfer, we also have no energy transfer. Energy transfer. So these are the kinds of systems we're looking at. And whenever you have a system, there's a couple of laws of thermodynamics that are going to apply to them. The first one is the law of conservation of energy. Let me write this a little smaller so I have some room. Conservation of energy. I'm sure you've seen this before. Basically, the change in energy of our system, which is the final energy E2 minus the initial energy E1, equals the energy I add to it, E in, minus the energy I remove from it, E out. So let's say I have a pendulum right here, okay? And if I just let this pendulum go, I'm not really adding energy or removing energy. So I know that the change in energy in this case has to be zero. So right now we know that it's high up, it has a lot of potential energy. Then it swings on down here and it's moving, it has a lot of kinetic energy, and eventually it'll come back up here. It'll have no kinetic energy, but it'll have lots of potential. They can keep going back and forth in this idealized case. They can also have things like just like a closed off system here. And if there's no outlets here and I just add some energy, maybe I heat it up or something, we'll see heat is Q. Then I know that the energy of the system has to increase because I have an E in but not an E out. The second law is about entropy and basically the directions that our interactions can go in. So you've probably seen a video on entropy, or maybe you haven't, or maybe you've heard of this. But when we're talking about the second law of thermodynamics, it's really about the direction that energy interactions could go in. So if I have some table right here, and I have a hot container, right? It's very hot. Then I can imagine that heat's going to come out, and this works for conservation of energy because the energy of this is decreasing and the energy of my outside is increasing. But if I had a case where the outside area is cold, or just room temperature, and the same thing with this cup, there's nothing stopping the room from getting colder and this hot from just spontaneously heating up, drawing heat out of the room. But obviously we know that doesn't happen, and that's because of the second law. There's some kind of direction that's involved with all of these energy transfers, and we'll take a look at that later on in thermodynamics. Now, with each system we can have, when we're looking at a specific case of that, it's all going to have properties. That's not a great way of saying this. Basically, whenever we have a system, just at some state, it's going to have certain properties that we can evaluate it with. And there are two kinds of properties that we're going to look at. We have intensive and we have extensive. So intensive means that it's independent of mass. And extensive means that it is dependent on mass. So let's go ahead and take our system and give it some properties. We know it's got pressure, temperature, volume. That should be good enough. And let's say I just take this and I just split it in half, okay? So I just go like this. On each side of this partition, I know that it's going to have the same pressure and temperature. But it will have half the volume. And so we say that volume is an extensive property because it depends on the mass. If I split it in half, it's going to half. While as pressure and temperature don't depend on the amount of mass that we have. Some properties that we can have are mass, volume, temperature, pressure. We can have density. Eventually we'll see other stuff like internal energy, entropy, enthalpy, things like that. So these, we'll talk about these later. But basically, there's lots of ways that we can describe our system. Mass is just how much stuff there is. The unit we have is kilograms. Volume is basically how much space it takes up. So it's cubic area. Meters cubed is what we use. Temperature is the average kinetic energy of all of the particles that are internal to our system. So there's lots of units we can have. We can do Kelvin, Celsius, Fahrenheit. Rankine is rarely used, but sometimes you'll see it. Density is basically how much stuff you fit per unit area. So we have kilograms, which is our mass, per unit. I said area, I meant volume. This is meter cubed. Internal energy is just how much energy is stored within all the particles. So it's different from temperature because you can have things other than just like the kinetic energy. And so all of that combined will give your internal energy, and the units here are joules or Newton meters. And lastly, we have pressure. So let's talk about pressure. Pressure is a little bit more involved than the other ones. Pressure. So pressure is defined as force over area, which means that its units are newtons, which is our unit of force, per square meter. And this is also the same thing as pascals. Now because pascals are kind of small, you also see we use the kilopascal a lot, which is just 1,000 pascals. So basically what this is saying is if I have some area and I apply a force to it, then the force per unit area is going to be my pressure. And now you could be like, okay, but what if there's a gradient of force? What if there's more force over here? And that's a good point. With our properties over here, we're basically assuming that it's well mixed and that it's something called homogeneous, which basically means that along each point in our system, we basically have a constant temperature, pressure, density, things like that. Anything that is intensive, we're assuming is basically constant across our whole system because it makes the analysis easier. Now pressure, when we're talking about a real fluid, is going to vary with depth because of gravity. So if you can imagine right here, if I've got a container, I've got maybe a fluid in here, maybe this is water or something. Above this, the air has a weight that's pushing down on this, which creates a pressure. And so this is the atmospheric pressure. We usually write it like this. Now this water, as I go deeper and deeper, it has to support the weight of all the water above it, which means as I go deeper, I get a higher water pressure. So this right here, maybe a slice of this water, has to hold up all the water above it, and so it has to be in equilibrium, to not be moving, it has to be basically pushing up against all of this weight. So if we go ahead and we take a look at a slice of this water, we'll have pressure from below, we'll have pressure from above, maybe we'll call this P1 and P2, we'll have pressure from the sides, and we'll also have a weight force of the water. So if it's in equilibrium, then we know that when we add up all the forces in the z direction, so let's be clear, the z direction is up. Maybe we'll call this the x direction, and then into the page will be the y direction. Alright, and then since we're taking a look at the slice of the water, this will be our delta z right here, this width of it. My bad, delta x, since this is the x direction. Our height will be delta z. And into this page will be our delta y. So if this has some thickness to it. Okay? So the sum of the forces in the z direction are going to be this upward pressure times the area of our slice, which we can see right here is going to be delta y times delta x. So we'll have P2 delta x delta y minus, in the negative z direction, we'll have this P1 times the same area, delta x delta y. And then in the z direction, we also have a weight force. So our weight force is mass times gravity. But since this isn't really a quantity that's going to be helpful with the other ways that we have things defined, we're going to, instead of using mass, we're going to use density, which is mass per volume, times the volume of this slice, which is dx, dy, dz. All of that has to equal 0 because we're in equilibrium. So now we can go ahead and just cancel out our dx and dy's here, since there's a delta x and delta y. My bad, I meant delta x and delta y for each of these. These aren't differentials in this case. And now if we go ahead and we add over P1 and subtract over P2, so essentially our change in pressure with height as we go from this lower depth 2 to 1, our change in pressure, delta P, is negative rho g delta z. And this negative sign just means that as we increase in height, our pressure decreases. If we were to go deeper, then we get more pressure. Now because of the way pressure basically acts on an object, if we have more pressure on one side of it than the other, so if a little pressure here and lots of pressure here, then this would create an imbalance, and we'd expect the object to shift in some way. And if it's in equilibrium, the only way this is going to happen is if at the same height, because of gravity, we have the same pressure. And so if we have an object like this, we can assume that it has the same pressure at the same height. And one thing you can do with that is you can take an object and have a very small area right here with a fluid and a very big area over here. And now if I apply a force here, since the pressures or the forces over areas have to be the same, a small area with a decent force will give us a really big pressure. And now since it has to have the same pressure over here, over a big area, we'll have a really big force. And this is how things like car jacks work. But this is also useful if we want to measure the pressure. So let's say I have like a barometer set up. So if I have basically a column like this, and over here I've got it hooked up to some device which has some pressure inside it, and then I have a water column right here at the same height as this with some height h, and I've got some atmospheric pressure up here. Well, since I know the pressure here has to equal the pressure here, if I can find the pressure here, then I know what my pressure inside this tank is going to be. And so if I know PATM plus my height times the density times G, remember that this height is going down, it's negative, which is why we're adding the pressure. This is going to equal the pressure inside my tank. So pressure, along with all the other properties of our system, at some point give us what's called the state, which is basically just a set of all the properties. So if I just have a box here, I've got pressure, I've got volume, I've got temperature, I've got all sorts of things. This right here is a closed state. And if there's equilibrium in the state, that means that there's no driving forces, so there's basically nothing's going to happen to it if I just let it go over some time. And this gets us to something which is called the state postulate, which is going to be useful when we want to solve for properties of our state. So for something which is called a simple compressible system, which is basically a system that doesn't have magnetic, surface tension, electrical, any effects like that, if we can get two independent intensive properties, then we can get the state, which means that we can get any of the other properties we want. So if I know pressure and volume, I can find temperature. I can find internal energy. I can find density. I can find any of these. Now, if we're going from one state to another, then that's called a process. So a process goes from one state up to another. And if we happen to know the closest state, then we can figure out basically what it's going to look like at each point along this process. If it's what's called quasi-equilibrium, which means that it's infinitesimally close to being in equilibrium as it goes across the process, then I can kind of draw out what the entire process looks like. If that's not the case, then I just know the initial and the final states, so I just use a dashed line to kind of indicate that it's going from here to here, but we don't know how. And the reason that knowing the exact path that it goes through is helpful is because then we can know the properties, and that allows us to do things that can tell us about the process. Like, for example, we'll see later that we can get work from the pressure and the changes in volume as we go across the path. But don't worry too much about this. Just understand the idea of the process and how basically this is going to be pretty useful when we think about, again, thermodynamics is all about things that are changing. We're talking about energy that's changing, heat added, work removed. So processes are really where things are at. We don't just look at things that are at one state. Now, lastly, we're going to talk a little bit about notation here, because it's something that's going to come up quite a lot. Two things I want to talk about are first, dot notation, and secondly, specific. So dot notation, some things you might see are things like m dot, q dot, w dot. All of these just mean per unit mass. Sorry, per unit time. I completely messed up there. Per unit time. So w dot means work per unit time. It's also called power. This should be a lowercase t, since capital T is for temperature. M dot would be mass per unit time, so this could be something like 3 kilograms per second. Heat is basically the rate of heat added per unit time. Now, specific is another terminology we'll see a lot, and specific means per unit mass. So my specific volume, which I write like this, it's the Greek letter nu. Technically, it'll look something more like this, but that kind of looks like a U and a V, so I write it like this. You might have also noticed that I write the volume with a line, and that's because we have volume, which is a capital V, and also velocity, which sometimes is written as a capital V, which is really annoying, but I think it makes more sense as a lowercase v. And just to distinguish all of these, volume gets a line through it, it's a little bit easier. Specific volume is volume per unit mass. So this is just equal to total volume over mass. We can have things like specific internal energy, which is our total internal energy per unit mass. Things like specific entropy, which is S. We'll talk about that later. Basically, if it means specific, almost all the time we're going to be talking about per unit mass. And so these are some of the basic ideas that we're going to be talking about as we're looking at applied thermodynamics.